So if we're going to understand the Piedmont Aquifer System, we have to understand flow through fractures, because when we get down into the bedrock, the flow of water is really going to be through the fractures. And there are several important characteristics that we have to recognize. One is the aperture of the fracture. What is the opening of the fracture? And what we'll see, so that would be the aperture right there. What we'll see is that the aperture is typically in the tens of hundreds of microns. So remember, 1,000 microns is 1 millimeter. So 100 microns, a tenth of a millimeter. A sheet of paper is about 75 microns. So the aperture of these fractures that the fractures that are going to contribute to groundwater flow are typically in the range of a sheet of paper or so. Another thing that'll be important is the fracture density. How many fractures are there in a unit of volume? So we'll think of fracture density in a variety of ways. One is that it's the area of the fracture surface per unit volume of rock. We could also think of it, though, if we look at the image shown on the left, that it's the length of the fracture traces shown on that image per area. And we can also think of it as the number of fractures along a borehole. Another important aspect will be the connectivity of the fractures, because an individual fracture is going to be somewhere in the range of a few meters or tens of meters long. But in order to form a flow system, we have to have multiple fractures that are connected together. And so the interconnectedness of the fracture will be important. And the key thing is whether there's a connected pathway that forms what's called a percolating network. So a percolating network is an interconnected network of fractures that is sufficiently interconnected to allow water to percolate through it. And also the mineral precipitates in the fractures and weathering products, those will be important because those will tend to plug up the fractures and reduce the permeability. So in general, what we're showing here over on the left-hand side is that there's a hydraulic head gradient from high head to low head going from left to right. That's causing flow. And I think as we see this example, we would expect that the flow would be along this fracture system here. That's the percolating network of interconnected fractures. And the rate of the flow through an individual fracture will be depending on the aperture and the filling. The overall flow of water, or the flux of water through this system, will depend on what the fracture density is and how interconnected those fractures are. So it's convenient to think of fractures as a slot with an aperture that is the separation of these two plates. A set of parallel plates, like I show in this ellipse, that's a convenient way to think about a fracture. We saw in an earlier video that fractures are really supported by asperities, so they really aren't like this actually, but we can conceptualize them as having kind of an effective aperture that is characterized by this length. And so we can then say fractures are this slot, and we'll want to characterize the fracture density. So there are a couple of ways of doing this. Um, I think that probably the best way is to think about a fracture area um, per unit of volume. So if the fracture is a break, and we've got two surfaces that are created that are in contact, we take that surface area and divide it by the volume. And so that's a good way to think about it, but that would be a hard way to actually measure because you would have to be able to image this fractured surface in a three-dimensional volume. But you could imagine more easily, I think, that there might be an outcrop with fractures exposed on it. And what I'm showing here is so this is supposed to be like either a vertical cut or maybe a horizontal surface, and these are fracture traces. So it's a three-dimensional fracture that goes into the plane, but we're just seeing the trace of it. And so one way that we might estimate the fracture density is by measuring the length of the fracture, that length, and summing up the total length per unit area. So that's one measure. That would be this measure here, the fracture length per unit area. And another way to think about it is that we would have, say, the fractures are uniformly spaced, like I show in that example, and I sample them along a line, that red line. And it could be that this is a borehole, and we look at the fractures that are intersected by that borehole, or maybe just a single traverse across an outcrop. But in any case, what we're going to get is the number of fractures per unit length along this line. And that would be another measure of the fracture density. And you can show that with some idealized geometry, the fracture area per unit volume is that these are equivalent for idealized fracture geometry. If the fractures are uniformly spaced and parallel, then this is true. If they're not, then these different measures will be somewhat different, but they're often assumed to be a good surrogate. I mean, for example, with the number of fractures per length, this is typically for subsurface characterization. This is the kind of information you would get from a borehole. So this may be really the only information you have about fracture density. Ultimately, the fracture density, all of these three measures end up having the same units as it's 1 over a length or 1 over a spacing. So you could think of it in 1D as the number of fractures per length. That has units of 1 over length. The fracture length per area, that has units of length per area. So that's got units of 1 over length. And fracture area is length squared per length cubed. So that also has basic units of 1 over length. So the fracture density will be thought of in that way. So we can then visualize, I think, that there's an important connection between fracture density and the connectivity. So the fracture density, we might expect there's a certain fracture density here, the fracture length per unit volume or per unit area, and we can see that the connectivity is actually fairly poor. Right here, the fractures are close together, but they're not actually connected. Same with right here. And so in order for water to flow along this fracture and make it out to this end, it has to go through that intact rock. Well, that might be very low permeability, and so the overall resistance to flow is quite high. And so if we take this fracture density and if we just increase it slightly, by adding one more fracture, then we have this connected network. So what's seen is that there's a kind of a critical fracture density where a percolation network of a certain size is formed. And below that density, you have individual fractures or pairs of fractures, but you don't have a big through-going interconnected network. And so there's an important connection between fracture density and connectivity. And the connectivity then is an important component of the overall hydraulic connectivity, or the overall rate at which water can flow through this fractured rock system. Okay, so in order to come up with a way to characterize the flow through fractured rock, we want to go and make use of this analog of fractures as two parallel plates. And if we do that, then we can take a look at the flow through an individual parallel plate or individual slot, and the flux through a single parallel plate like this is going to be equal to the head gradient times this stuff here. That's the aperture cubed. This is the viscosity of water and the unit weight of water. And then this is the fracture density. So in an ideal case where there's only one fracture, lambda would be 1, and we end up with then something that is, well, if you just look up the equation for flow through parallel plates, through a single parallel plate or a single slot-like conduit, you'll end up with something that may reduce to that. And then what we've added here is this lambda term to account for multiple fractures. Okay, so this term, or this expression up here, is the expression for the flux driven by a head gradient through multiple fractures that are characterized as parallel plates and characterized by this fracture density. And we can see then that this is, if we call that K, then this is just simply Darcy's law, where the hydraulic connectivity is given like that, is effective hydraulic connectivity. And so this is called the cubic law because the hydraulic connectivity depends on the cube of the aperture. It also depends on the fracture density and these properties of the fluid. Well, I should say these properties of the fluid. The 12 is there because it's the property of the slot-like geometry. Okay, so this is actually one version of the cubic law. You can also write it slightly differently without the fracture density, and in that case, this would be equivalent to a transmissivity. Okay, but I write it this way intentionally because what I want to do is show that there's this direct analog to the hydraulic connectivity and Darcy's law. And what that means is that if we're going to conceptualize, if we're working with a fairly large region where the fracture system can be just treated as a single fracture density, and we have an effective aperture here, then we can think of a flow through a fractured system, shown by this rectangle, as having an equivalent porous media that's characterized by this hydraulic conductivity. And that's important because that would allow us to analyze flow through a fractured system using models like ModFlow that are based on porous medium. This hydraulic conductivity is viewed as the effective hydraulic conductivity or the effective porous media analog to this fractured system. And then this is what we conclude. So what this also leads to is that we can, well, the first thing that it would do is lead to the conclusion that we could represent fractured systems, at least the flux, the large scale flux through fractured system using Darcy's law and using an equivalent hydraulic conductivity. What it also suggests, though, is that the hydraulic conductivity that we develop by doing this will depend on the direction. So I think from this simple example, we can see that the hydraulic conductivity that we might develop from this in this direction would be quite different than in this direction. In this direction, we're going to flow through this fracture. So if we say that this is the x direction and this is y, then kx will be much larger than ky, because ky with this system that we've drawn, ky, there is no connected fractured network in this direction. So ky is just going to be controlled by the permeability of the intact rock, whereas kx will be controlled by this connected percolating fracture network. So we would expect then to characterize fractured rock using equivalent anisotropic hydraulic conductivities or permeabilities, as I show here. Now, that's pretty easy to evaluate, or it's somewhat easy to evaluate where we would have layered sedimentary rocks, for example, because we would expect that the anisotropy would be oriented parallel and perpendicular to the sedimentary layering. In metamorphic rocks, one of the challenges is to just determine what this orientation is, what this orientation is, because it can be somewhat of a challenge to be able to figure out what the primary direction of connected fractures is at a particular location, and it may change quite a lot spatially, horizontally or vertically. So even though this is a good way to think about the effective hydraulic conductivity in fracture rock, often it's difficult to characterize what these different values are. Although it certainly is possible, and people have done this using well tests where they have several different monitoring wells, and they can tell then the hydraulic conductivity in different directions by analyzing these well tests. So to summarize, we can use concepts from porous media for fractured media by using this principle of the fracture density and some other principles that I've summarized here. So the porosity shown here is the fracture aperture times the fracture density, and that's assuming that this would be the fracture porosity, the porosity due to the fractures. So this is not including the porosity from the rock itself. The hydraulic conductivity, we just saw that would be summarized here, and we can have a specific storage that is the fracture density and this is the change in the aperture per change in pressure head. And that's something that could be measured with a borehole extensometer, for example. And what this is doing is recognizing that the specific storage of a fracture depends on the compliance of the fracture and how readily it moves, how readily the aperture changes um, in response to compression or extension of those asperities that we saw that were holding the fracture open. Okay, so this is important because these are all the properties that we need to know to characterize the flow of water through an effective porous media that represents a fractured media. So we can use those principles of characterizing fractured rock as an equivalent porous media and apply them to the results that were developed by Malcolm Schaeffer when he studied these various different power plants in the Piedmont. And what Malcolm came up with is the profile of the hydraulic connectivity determined using well tests and plotted as a function of depth, or really as a function of the different zones. So the M1 data are shown here along this line, M2 transition and fractured rock. And you can see that among these 7 sites in foliated rock, there's a good bit of scatter, but the envelope of hydraulic connectivity looks something like that. So kind of zigzags, a bit higher in general in the transition zone and a bit higher in this M1 saprolite zone, but a good bit of scatter and a good bit of overlap in the hydraulic connectivity between these different zones. Now, there are four locations that were studied that are underlain by plutonic rocks, and these are the profiles here. So to compare them, what I did was to take this envelope and that I show here in blue and apply it down here on this scale. And you can see that that envelope includes most of the measurements that were made in these plutonic rocks. The one difference would be this green plot here, particularly at shallow depths at the Gaffney site, and then maybe also this one at McGuire. And I guess here in the fractured rock, there's also some measurements that are a good bit lower than this envelope, and that I guess is consistent amongst all of these sites. So there certainly are some differences between the plutonic and the foliated. One thing that Malcolm wanted to evaluate was whether these differences in the hydraulic connectivity in the different zones were statistically significant. So he took these the populations of measurements and compared them statistically. There's the envelope for the plutonic rocks, and here's the overall profile, and this is the average of all of the different sites, and the green is the envelope. So you can see that down here in the transition zone, the overall average envelope it's about an order of magnitude. And then as you get to shallower depths, it's a bit more than an order of magnitude because the envelope has this low end defined by the one or two sites there for the plutonic rocks. But nevertheless, what we see is that 10 to the minus 6 is a pretty good estimate of the average hydraulic connectivity. And on average, the transition zone is a bit higher hydraulic connectivity, maybe 3 to 4 times 10 to the minus 6 meters per second for the average hydraulic connectivity. But the envelope is pretty large, and so the question about whether these are statistically significantly different is an important one. And Malcolm addressed this by doing a series of statistical tests, much like a t-test, where it compared the hydraulic connectivity in one zone in the transition zone and compared it to the mean values for the overlying M2 saprolite or the underlying fractured rock. And what he found was that these are the different sites, and R means that, well, from hypothesis one, that's shown down here. So in hypothesis one, A means that the mean of the transition zone is statistically different and greater than the means of M2 and M and D. So for the A's, this site, that site, that site, that means that the transition zone is more permeable than the rocks above and below it. And at the sites that are R, that means it's not statistically different. So the mean may be higher, but the overlap is great enough so you can't say that it's statistically different. And what you see in general is that it's about half and half. So I think the take-home message is that the transition zone could be more permeable than the saprolite or the underlying rock, but it also maybe not, maybe it's not. At least it can't be demonstrated to be in a statistical sense. So that's, I think, some good insights about the transition zone and whether it is indeed a more permeable zone than the overlying and underlying zones. So this is another set of data from the study by Malcolm Schaeffer. It shows the number of fractures as a function of the thickness of the transition zone and the linear fit to these data. And so you can see that the number of fractures increases with the transition zone thickness. And you can also see this gives you a nice depiction of the transition zone thickness. So you can see that all but 3 of the sites have a transition zone that is, that's about 16 feet or so, or less. So 16 feet, maybe, let's say 5 meters, that would be a good estimate for the thickness of the transition zone that would work fairly well, except for these sites here, where there would be exceptions. And then in terms of the number of fractures as a function of the thickness, we see that they increase, and the slope of this is 3.3 fractures per foot from this core study. And so that gives us some insights about the fracture density. Remember, we said there are a variety of ways that fracture density could be determined, and the number of fractures per length is one of them. So in the transition zone, this gives us an estimate of roughly 3 fractures per foot as the fracture density in the transition zone. Another aspect of the geology in the Piedmont is the distribution of the different units. Now, keep in mind that the units that we've been looking at are all varying degrees of weathering of underlying parent rock. And so these are determined from drilling, and you can correlate between the boreholes and come up with what the structure is like. So I've got a few examples here that were developed by Malcolm Schaeffer, and they show just some examples of the distribution. Now, I should put this in context because if you look back through published studies, some studies say that the weathered zone, the saprolite and transition zone, is thicker above the upland areas and thinner above or below the lowlands. And some say that the reverse is true, that the weathered zone is thickest underneath the underneath drainages, and it's relatively thin in upland areas. And so those studies were based on probably a smaller sampling of the sites compared to what Malcolm Schaeffer had to look at. And so when you put it together, well, here's some examples. We can start off just by taking a look at this set of cross sections from the Bridgewater Linville site. Now the yellow here is the saprolite, and the dark blue is what Malcolm calls sound rock, and then these pink and green are different variations of weathered material. The pink is weathered fractured rock, the green is weathered rock, and the blue is also some transition between the two. The legend here is a little bit too small to read. And what you can see here is that so this is an upland area up here on the right side, and it's a bit lower elevation here. And so you can see that we've got thickness of weathered material like that, and then it's a good bit thinner here in the more low-lying area. So this is a place where the weathering thickness is greater in the upland areas, and it's because the topography is higher, but also you can see that just the depth of the weathering is greater over here on the right side where the elevation is higher. Well, if you look at some other cross sections, though, it's a little bit less clear. Here, this is some uplands, and this is a little bit lower. And I guess you still have a similar kind of effect where the thickness is greater here than here, but it's less developed than it is in the view that we see in the cross section above. Here's some other examples from the two sections from the Oconee site. And so here's the lower lying area. There's not really a stream here, but it is perhaps a drainage. And you can see in this case that it's a little bit ambiguous. Well, I guess, I mean, here's a little bit of a drainage here, but pretty small compared to there. The thickness decreases here, so it is thinner over that small drainage, but it's just a very slight drainage. And then it gets much thicker here, and then thins a little bit here. In over this one, section B, though, you can see that this low-lying part of section B is the thickest. It's thicker than here. So there is perhaps some evidence that in places the weathering gets thinner underneath underneath drainages compared to uplands, but there are exceptions. Look here, there's a place where it's just fairly level, and the thickness of the weathered zone is relatively thin. So I think that there's a good bit of variability, and it's probably difficult to generalize how the thickness changes over the landscape, the thickness of the weathered zone. And, I think this probably makes sense because the degree of weathering is, well, the weathering in general is the reaction of the rock to water and to oxygen. And so it's going to depend on how readily reactive water can interact with the rock. And so that'll depend in part on the flow system, but it also depends on the distribution of the rock type and how reactive, how susceptible the rock type is to weathering. So in one case, the degree of weathering, you can see how it would depend on the flow system, and I mean, you might have something. You might imagine that there's a flow system here that looks like this. If there was in fact a drainage down here, stream. And so in that case, you could imagine that here this downward flow would cause additional weathering right here. But you could also imagine that the rock type is highly variable, and that the rock type along this flow path may be the resistance to weathering may be quite variable, and that would cause a good bit of variation in the depth of weathering. So probably hard to generalize. I guess here's some additional examples from the Catawba site about the, the variation in the thickness of the weathering. So to summarize from these insights from Malcolm Schaeffer, he provided this objective distinction between different units based on the statistics of sampling that are intended to characterize the degree of weathering and fracturing. And he recognizes these four different zones: a saprolite and a weathered rock that is kind of grouping in with saprolite, the intact rock, and then a transition of fractured rock that's perhaps not weathered enough to be deemed weathered rock. And these could all be identified based on the statistics of sampling, the number of blows per foot for split spoon sampling, or the RQD. And in general, the transition zone is more permeable than above or below. Statistically, it was about half the sites could show that it was statistically different. The others were less definitive. So I guess rather than saying in general, I would say on average. And we saw that average plot. On average, the transition zone is more permeable than above or below. Statistically, though, you could show that it was statistically different than the zones above and below in about half the sites that were tested. And there's a high degree of lateral variability in the thickness of the weathered zones, and in some places the weathered zones are absent locally, although that's really fairly rare. Okay, so what we've seen from those field studies were the characteristics of the rock at the field scale. You can also take cores of the rock and measure it in a laboratory. And when you do that, you come up with some much lower hydraulic conductivity. So this column shows the hydraulic conductivities for these different metamorphic rocks in units of meters per second. And you recall that the typical value that we saw from the study by Malcolm Schaeffer was around 10 to the minus 6 meters per second. And here the rock itself is a 10 to the minus 11 to 10 to the minus 10 in that range. So 4 or 5 orders of magnitude less hydraulic conductivity than for the fractured rock in the field. The specific yield, in general, 0.017 is the large end, and 0.007 to 0.017. These rocks have a porosity of there's 1.5% to almost 3%, and the specific yield is say roughly half of that. Here it's pretty similar, but half to roughly maybe half to 3/4 of the porosity. But in general, the porosity is quite low for these crystalline rocks. So what we can see from this is, I guess, one is that these crystalline rocks have hydraulic properties, specific yield and hydraulic conductivity and porosity that can be measured, can be characterized. They're quite low, and they're very low compared to the the field measurements, because the field data are characterized by the effects of fractures that don't really show up in standard laboratory measurements. So to kind of summarize the bulk fractured rock, this is the range 10 to the minus 6 for saprolite and the underlying fractured rock, and maybe approaching, well, I guess we saw 4 times 10 to the minus 6 for the average value in the transition zone. And then these are the values for intact rock. The transmissivity, this is kind of a typical range for transmissivities. Recharge, so probably a typical value, at least around Clemson, would be say 0.1 meter to maybe 0.2 meters per year. And if we go over the whole Piedmont, we get a bit of a broader range. This well yield, this is from a USGS report, and this is probably an estimate of the well yield in an area. This would be the high end of the well yield. A well that can yield 30 gallons a minute is really quite rare in the Piedmont, and even 30 gallons a minute that's pretty unusual. So these are probably the high end well yields for a particular region. In a lot of cases, well yields will be much less than this, and more in the 1 gallon per minute range. That would be, I would say, more typical, and these would be the real high yielding wells.